Okay, so welcome everybody back. Today we are happy to have Yakov Kononov from Columbia University, who's going to tell us about the geometric construction of quantum difference equations.
Thank you very much for the opportunity to give a talk here. It will be mostly based on our joint work in progress with A.Smirnov, who is also here. And the talk will be very informal. Feel free to interrupt me and ask questions anytime. So a class of quantum field theories called N=4 three-dimensional theories has been attracting growing attention recently. And one of the most important feature of such theories is the three-dimensional mirror symmetry. So basically it means that for any theory T, there is some sort of dual theory, and the correlation functions are the same in two theories. So they are just two different languages to describe the same phenomena. And it has a lot of mathematical applications, especially in geometric representation theory. So in low energy limit, quantum field theory is described by modulated vacuum that is a map to some variety, usually holomorphic symplectic varieties if we have enough supersymmetries. And this means that for two such varieties, for two modular space of vacuum for two different dual theories, enumerative invariants should be connected in some non-perturbative way. The most fundamental enumerative invariant of them is the so-called Vortex function. It is a certain equivariant count of rational curves in a variety. It satisfies Q difference equations in equivariant and Keller variables. And roughly speaking, three-dimensional mirror symmetry permutes equations with respect to equivariant and Keller variables. Let's discuss more rigorously what 3D mirror symmetry is. So we have a pair of symplectic resolutions of singularities. So for a variety X, the resolution of singularity is controlled by a parameter, a real parameter theta in the second cohomology of X. Also, we have torus acting on X. I denote by X, by A, the torus preserving the symplectic form. And also I introduce one-dimensional torus C star H, which scales the symplectic form by H. And since we have to deal with Keller variables as well, we introduce Keller torus, that is the Picard group with coefficients in C star. So, and denote the same data for the dual variety by the same letter with factorial. And let's impose the following assumption, that the sets of fixed points of X and X factorial with respect to the corresponding tori are finite. This is not necessary, but working in more generality requires us to overcome significant difficulties. So let's focus on this case. And it includes a lot of different examples, such as Nakajima-Quiver varieties of finite and affine type, resolutions of slices in affine Grassmannians of AN type, Bow varieties, and so on. So we say that varieties X and X factorial are 3D dual if first of all there is fixed isomorphism kappa between equivariant tori of one variety and Keller tori of the other variety. So we have a map kappa from A to K factorial, from K to A factorial, and also some transformation of the H bar, the torus acting on the symplectic form. So informally, it exchanges equivariant and Keller tori. So we have fixed theta and theta factorial, which came from the resolution of symplectic resolution of singularities, and by the map such theta, it belongs to the Lie algebra of the corresponding Keller tori. And we have map kappa from A, from the equivariant tori to K factorial, for example, and we can consider the differential of this map. It is the isomorphism between Lie algebra of A and the second cohomology with coefficients in R. So we can take the pre-image of theta. It defines as some element of the Lie algebra of A, some sigma. And similarly, we construct sigma factorial for the dual variety, and they define as the compositions of the tangent spaces to X and X factorial to attracting and repelling directions. This depends on the chamber to which sigma and sigma factorial belong. So as usual, define attracting set of a point P to be a set of points such that the corresponding flow, the flow corresponding to sigma acting of that point, in the limit you get P. And then take a closure of such such varieties in the graph, and so we have then the full attractive set to be the smallest closed subset, which is closed undertaking attractive, and it defines as partial ordering on fixed points. So the second assumption is for 3D mirror symmetry is that there is a bijection of the fixed points, and it inverses the partial order. Later it will be clear why it should reverse. So let's now talk about equivariant elliptic cohomology. For that we need to introduce the elliptic curve, that is C star modulo Q to the lattice, one-dimensional lattice. And there is the functor of equivariant elliptic cohomology. T equivariant elliptic cohomology of a point is T modulo Q to the co-characters of T. This is rank dimension of T, abelian variety. And since we deal also with Keller variables, consider extended equivariant elliptic cohomology, that is multiply it by the elliptic cohomology, the T factorial equivariant elliptic cohomology of the point. M.Aganagic and A.Okounkov constructed elliptic stable envelopes. That is a section of certain line bundle over the extended elliptic cohomology scheme. And we need the twisted version of it. We multiply the stable envelope of P by the elliptic Tom class of the repelling direction to P factorial. And if we define it this way, then we see that on the diagonal, the values are the same. So stable envelope of point P restricted to P is the same as stable envelope of the point P factorial restricted to P factorial. So the third and the most important requirement for 3D mirror symmetry is the existence of some line bundle over the scheme elliptic t times t factorial equivariant cohomology of x times x factorial. And a section of this line bundle such that, so we have maps from extended elliptic cohomology, extended T elliptic cohomology of X to this big scheme, elliptic cohomology T times T factorial of the product of varieties. It corresponds to a restriction of a class to a point. And the same we have for a dual variety. Then the pullbacks of such section it should give us elliptic equivariant cohomology of varieties X and X factorial. So the pullback under inclusion with respect to P factorial should give us stable envelope of P and vice versa. There are lots of examples of it. For example, T star of Grassmannian if K is less or equal than N over 2. And the dual variety is also quiver variety shown on the picture. So it's a linear quiver with two framing vectors, with two framing spaces located at points K and 2n minus K. And dimension vector is 1, 2, 3, and so on K, then K, 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 and then it's decreasing from K to 1. And more generally, we can consider a T star G mod B and T star of the Langlands dual of G modulo the Langlands dual of B. And also a very important example is the case of the Hilbert scheme of n points on C2.
When you say that these are examples, these are examples of what? Do you know the entire structure of this mother function, or just the statement of 3D mirror symmetry, or what? What are we exemplifying?
So the case of T star of Grassmannian has been worked out by A.Smirnov and collaborators, and this example is known in details, in particular the structure of the mother function. And for Hilbert scheme, this is, I assume, a work in progress of you with A.Okounkov, right?
I'm not working on it currently, but okay, yeah. So only for T star of Grassmannian is the structure known? I mean, this mother function?
Yes, I think okay. So. Let's define now another normalization of elliptic stable envelopes and put them to a matrix. So we normalize so that we get 1 on the diagonal. And so we get upper triangular matrix where in rows we have fixed point components of elliptic stable envelopes of points. Then it follows that if we apply kappa automorphism, then this matrix for the variety X and the dual variety is related by this way. And it is some matrix of elliptic functions, and we will now consider various limits of this matrix. But let's first consider the basic example of this function f of z and a. This is the section of the Poincare bundle over elliptic curve times the dual elliptic curve. So let's consider.
Yakov, maybe I should just say for physicists what one is trying to construct. So what I'm studying here is a three-dimensional theory on a torus times an interval. And one wants to say that studying the 3D theory and its mirror with sort of pairs of Dirichlet and Neumann boundary conditions on the two boundaries are exchanged by mirror symmetry. So mirror symmetry also exchanges Neumann and Dirichlet boundary conditions and the pair of 3D theories, or equivalently the Higgs and the Coulomb branches. So these elliptic functions should be elliptic general of the effective two-dimensional theory you get. And if the theory is an abelian gauge theory, then one can construct this explicitly physically, more or less. But in other cases, I don't know. So and one sees nicely the action of mirror symmetry.
Mina, I'm sorry, may I ask you to repeat in more details what you have just said? So first of all, you begin with a four-dimensional theory and D3 branes, which are
three-dimensional theory. Three-dimensional.
I'm sorry, don't you want a Hanani-Witten to begin with?
No, actually, and so one of the questions is to make these brane realizations actually more useful for this kind of a problem. So in fact, for an abelian gauge theory, you don't need any of it, and you can sort of solve the problem essentially in its full generality, right? And understand that the structure exists, okay? But beyond that, I don't know, okay?
I'm sorry, I'm asking a very basic question, how to arrange branes so that these functions will emerge. It's in your papers, but I'm sorry, I don't remember. So
in fact, it is not. I mean, the story is more general than anything that can come out from these brane constructions, right?
But just to have a simple example, for example, for cotangent bundle to Grossmanians.
We're trying to get examples off, right? If you want to be able to read off the effective two-dimensional theory whose elliptic genus this is going to be, okay? I don't know a way of making the brane constructions useful, because the brane construction will give you the three-dimensional theory, and you're supposed to go further and put that three-dimensional theory in an interval with a pair of boundary conditions. Okay, and then the structure gets more complicated. I think there should be a way, right, of getting some like direct physics insights on this, but it's an open problem.
So may just for a few more seconds. So first of all, you squeeze D3s between NS5s and D5s, and this gives you a 3D theory with the target being cotangent bundle to Grossmanian. Now, you want to do another squeezing along a different direction. And these boundary conditions are of different kinds. One will give you stable envelopes, and the other will give you stationary points. So the entries of this upper triangular matrix that Yakov put there should correspond to the second squeezing. And then so you're left with 2Ds, which you put on a torus and compute your partition function. So now you would think that mirror symmetry would exchange the sandwich of Hanani-Witten and also the second sandwich. So then the stable points will become envelopes, and envelopes will become stable points. So this makes a lot of sense to me. Okay, thank you. Sorry for a long interruption.
So this is supposed to be an interactive talk, so please also others just go, feel free to ask questions. And Yakov is going to bear with us.
Because I think that we have a similar situation in what we're doing with Alexei, except that we're doing it right now for Hilbert's scheme. But we could also do it for, I think, for cotangent bundle to Grossmanian. We have this double squeezing arrangement, in a sense. Okay, sorry.
Thank you very much. So we will consider various limits of this matrix in equivariant and the Keller variables. And the basic example to work out here is this function for the Poincaré bundle. So Z and A are coordinates on elliptic curve and the dual abelian variety. So if we substitute instead of Z times Q to some power S, and then take a limit when Q goes to 0 and keep A fixed. then the situation is different for integer s and not integer s. So for if s is not integer, the answer is a function of only a. And if s is integer, we get a ratio of 1 minus za over 1 minus z. And this happens because of the following. If we expand theta function, I forgot a prefactor here, of q. So we get this expansion, and then we substitute x equals to q to some power. And let's see the leading term with respect when q goes to 0. If s is not integer, then there is a unique minimum of this quadratic function over integer numbers, and that's why we get a monomial. And if s is integer, then two subsequent integer numbers give you a minimum of this function, and that's why we get something like 1 minus za. So we have the following conclusion of this example, that the limit is a piecewise constant function of s, and it changes only when s crosses certain walls. In this example, they are located at integer points. And for regular slopes, that is outside of walls, the limit does not depend on, it's a mistake here, it should be on z. Okay, and the theorem of Mina and Andrei is that if we take L to be a generic line bundle in Picard times R, then the limit of this matrix T that I described is a piecewise constant function of L. It changes when L crosses certain walls. Walls is some hyperplane arrangement on L. Basically, it's values of z that appear as monomials in theta functions in this matrix T. And for regular values of the slope, the limit does not depend on Kähler parameters and gives us k-theoretic stable envelopes of the slope corresponding to the line bundle L in the same normalization, so that we have one on diagonals. And let's define for an element W of a Lie algebra. So now I switched for a moment from Kähler variables to equivariant variables instead. So and let's consider some shift of equivariant variables that is given by W. W is an element of a Lie algebra of a real element, and define the corresponding cyclic subgroup of the torus generated by that element. Let's define the resonant set of X to be values of W, so that the fixed point set for that cyclic subgroup is larger than just a set of all fixed points. And this is some hyperplane arrangement in the Lie algebra of A. And we proved that 3D mirror symmetry switches walls with resonances of the variety and the dual variety. And similarly, the limit when we shift the equivariant parameter, the limit when Q goes to 0 is a piecewise constant function, which changes on the resonance set. And for generic W, such a limit gives us k-theoretic stable envelope of the dual variety, and it depends only on Z. So this theorem it follows just formally from the theorem of Mina and Andrei by applying 3D duality, 3D mirror symmetry. And now let's discuss what happens when we consider a limit to a wall. So if we have some line bundle L, a real line bundle, which is not generic, but it is on a wall, and L prime is arbitrary line bundle in infinitesimal neighborhood of L, then we can compare such limits to L and L prime. We know what happens when we take a limit to L prime. We get K-theoretic stable envelopes. And we proved that if we consider limit now to L, to a wall, then we get a product of two matrices. One of them is the matrix corresponding to L prime, and the other depends significantly only on Z. But more precisely, the matrix that we get here as a first factor in the limit is the conjugation of the matrix depending on Z by the bundle defined by L. L is some fractional bundle, and this operation is conjugation by the operation of classical multiplication by L. So it is, so the matrix Z double prime, it depends significantly on Z, and with respect to A, it is just a monomial. And let's discuss now how to describe this matrix depending on Z. What does it have to do with the dual variety? So let's consider small infinitesimal neighborhood of 0 in the real second cohomology of X, and consider walls passing through 0. This is some, it decomposes it to chambers, and two chambers are distinguished corresponding to ample slopes and to anti-ample slopes. So let's do the same for the dual variety, to take just chamber C that we obtained from sigma in the beginning. So from the construction, we already fixed the equivariant chamber, so we can apply the differential of kappa morphism, and it defines us some canonical chambers on the Kähler side of the dual variety. So if some element L is in walls of X, then kappa of L is in resonances, and then it corresponds, kappa of L, it corresponds to some non-trivial subvariety in X factorial, because there is some cyclic group corresponding to kappa of L. So then it turns out that if L prime is just L plus epsilon, where epsilon is the shift in the ample direction, then the corresponding matrix Z prime or Z double prime is conjugate to the K-theoretic stable envelopes of that fixed subvariety YL with small ample slope. So we consider a subvariety of the dual variety corresponding to the cyclic group defined by L. So it's more precisely, it is conjugation by some diagonal matrix. Oh, it stopped working. Sorry. Yeah, more precisely, it is conjugation by some diagonal matrix which depends of H, the matrix of K-theoretic stable envelopes of the fixed invariant subvariety of the dual variety. And similarly, if we consider equivariant limit to a wall, to a resonant point, then by this procedure, we can extract K-theoretic stable envelopes of the invariant subvariety of X of slope 0. For this construction, we don't need 3D mirror symmetry. We just have a variety X, and this is the answer how to extract K-theoretic stable envelopes of slope 0 of the subvariety invariant under cyclic group from elliptic stable envelopes of the big variety X.
Are you going to tell us what these subvarieties look like?
I will tell you about the main example, about the case of Hilbert scheme. Okay, and this, what does this construction allow us to do? So we have so-called wall R-matrices. That is, if we consider epsilon to be infinitesimal shift in the ample direction, then we can take arbitrary element on a wall and consider the relation between K-theoretic stable envelopes of slope L minus epsilon and L plus epsilon. And the theorem that follows from that limit theorem is that the R matrix for the original variety of some slope S is the same as the inverse to the R matrix of the slope 0 of the subvariety of this fixed subvariety of the dual variety. So this follows. Do I? No, I don't have it. If we write two different limits, so limit of elliptic stable envelope of Z times Q S and A Q to 0, we can factorize by two ways to have Z like ample, like ZS plus epsilon, A S plus epsilon, and this is equal to Z corresponding to S minus epsilon times A S minus epsilon. That's why the one of the R matrices Rx of S and sigma is the ratio of A, and Rys of 0 and of 0 is the ratio of the matrices Z in this equation, and it follows that they are similar. And let's consider now the main application. That is the case of the Hilbert scheme of endpoints on C2. As I said, this variety
Yakov, can you say this point just a little bit slower? Just the previous one.
Oh, okay.
Yeah. So, I should be able to say, but I don't. So
maybe let's go here again. So we have this factorization property. So the limit when Q goes to 0 of the matrix with shifted Z and L is not generic, this limit factorizes to a product of two matrices. The first matrix corresponds to the dual variety, and the second matrix corresponds to the original variety, to the stable envelopes with slope L prime. And in case when the shift L prime is canonical or anti-canonical, Z double prime is conjugate to the slope 0 stable envelopes of the fixed subvariety of a dual variety, and A is just stable envelopes. So we can write this. Let's now use the next theorem, that Z prime is the stable envelope for the dual variety. So we can now write limit Q to 0 of elliptic stable envelopes Q to L and A. This is equal to like a stable envelope of the X factorial L invariant subvariety and D plus times stable envelope of X and slope L. L plus epsilon. Epsilon is in D plus. And also we can write it down. We can write.
It knows about the other side, I said.
Okay. So if we compare now, then the ratio of, then one R matrix is equal to the other R matrix. So it allows us to construct, to translate action of certain quantum algebras on one side to the dual side. And let's consider the main example, Hilbert scheme of points of n points on C2. As I said, this is a self-dual variety, but this needs some still clarification. But let's assume that. So there is cyclic group, which acts by roots of unity, and it preserves the symplectic form. Okay, let's first say that Picard group is one-dimensional, since we have just a single vertex, and it is generated by the tautological bundle. And set of walls for the Hilbert scheme is the set of rational points A over B, and B should be less or equal than N. Then on the dual side, we should consider the fixed subvariety for the cyclic group of order B. And this cyclic group acts by matrices on C2 as exponent of 2 pi I over B and exponent minus 2 pi I over B. Then the fixed subset, the fixed subvariety of the Hilbert scheme with respect to this section is the cyclic quiver, the Nakajima variety corresponding to the cyclic quiver in some stability condition. This is the Hilbert scheme of points on the resolution of singularities on of AN surface, or an minus 1. The K-theory of such a variety for the cyclic quiver is the Fock module for the quantum group UH bar of GLB hat. And stable envelopes with small ample or anti-ample slopes, they correspond to standard and co-standard bases in the Fock representation for such algebra. Then we get as a corollary the conjecture of E.Gorsky and A.Negut that the wall R matrix for the slope A over B for the Hilbert scheme is conjugate to the transition matrix from standard to the co-standard basis for the Fock module of this UHGLB hat. And let's now talk about quantum difference equations. So the vortex function satisfies certain Q difference equation, and let psi be its fundamental solution. And then psi of QLZ times the operator of the classical multiplication by a bundle L is equal to ML of Z, some operator that is.
So yeah, Yakov, just maybe for physicists, tell them that what this vertex function is physically.
Physically, vertex function is when we consider maps from a Riemann surface to a variety which are non-singular at point infinity. For example, this we consider equivariantly, where we have U1 action on the base and action of some torus on the target. Denote this space by QM infinity. Since such maps are defined, the evaluation is defined at infinity, then we have the push forward to X. This evaluation of this map at infinity. So we can take a push forward, that is count rational curves with certain boundary condition at infinity, and the boundary condition is fixed by some k-theoretic class of the Nakajima variety X.
Physicists study this as they call them vortex partition functions, I guess after Gukov and others. They're basically partition functions on a disk times a circle, where the infinity is the boundary of the disk.
Yeah, thank you very much. So, such functions satisfy certain Q difference equations. Let's write down this equation as psi of z shifted times the operator of classical multiplication by some bundle L. This is equal to some operator times psi. And this comes from the following. Psi is operator when we consider two different types of boundary conditions at 0 and infinity. At 0, it's called the proper boundary condition, the relative boundary condition. So the evaluation map at this point is defined and proper, and at infinity just non-singular. And when we shift variable z, it is equivalent to inserting certain classes to 0 and infinity, and then by usual deformation theory, we can break this curve to a nodal curve. And so we have at one point still relative condition, and at one point we have non-singular condition. So then the operator of the first part of the curve with the relative boundary condition, it corresponds to the operator M of Z. And where we have non-singular boundary condition, this insertion is more elementary, and it corresponds to the classical multiplication by L. So, and this operator is known to have a factorization. This operator can be viewed as, if we draw the picture of walls, the wall arrangement in the Keller torus, it corresponds to a map from some point S to point S plus L. We can join these points by some path, and when we cross the walls, we apply certain wall crossing operator. And let's denote this operator by BW of Z, and it has certain poles with respect to Z. Then if instead of the operator of quantum difference equation M, we consider the monodromy of Z, that is transition from Z equals to 0 to Z equals to infinity, or equivalently, it is some renormalized product, infinite two-sided product of operators of M, or a two-sided product of operators BW along the path which is infinite line on this picture. So, and the idea now is, so monodromy is known to be the elliptic R-matrix. This was proven by Mina and Andrei. So it's a purely geometric object. And the idea is to get BW of Z, wall crossing operators, as certain limits of the monodromy. So, and for example, if we consider the wall crossing operator for the Hilbert scheme of endpoints on C2, then if we write it in the stable basis for the slope A over B, this operator coincides with the R matrix for the variety corresponding to the cyclic quiver. So it's the R matrix for the quantum toroidal algebra UH bar of GLB double hat in the basis of fixed points. And here is some kind of explanation. The monodromy is such transformation of elliptic stable envelopes of the variety and elliptic stable envelopes of the flop variety. So if we just apply elliptic stable envelope, we get from the solution regular at z equals 0, we get a solution regular at a equals 0. And similarly stable flop, it maps solutions regular at z equals infinity to solutions regular at a equals 0. So this contraction, this elliptic R-matrix, it sends solution regular at z equals 0 to the solution regular at z equals infinity. And it is a monodromy. So then such limits of the monodromy, we can use limits of the elliptic stable envelopes that we discussed previously. And then the answer for the limit of the monodromy is based on the factorization of elliptic stable envelopes. So let's consider such a limit. One stable envelope, it factorizes two stable envelopes okay. At the right hand side, it corresponds to stable envelopes of the opposite chamber of X dual and stable envelope and the fixed subvariety of X dual and stable envelope of X K theoretic with the slope L plus epsilon. And the other corresponds to the other is we have C instead of C instead of minus C because it is now flop. The first part of this formula. So it is different theta. That's why we get different chamber on the dual on the 3D dual side, and L minus epsilon slope L minus epsilon stable envelopes of the variety X. So this full product, we consider this product of four matrices. If we now write it in this stable basis, then the first multiplier and the last multiplier cancels. So the middle part here is the operator written in the basis of stable envelopes. And it coincides with the R matrix for zero slope of the dual variety, of the fixed subset of the dual variety. And similarly, we can construct shift operators by considering instead of monodromy that is stable, elliptic stable envelopes and the flop variety, we consider stable envelope and the stable envelope for the same variety with the opposite chamber. So that's what I wanted to talk today. So if you have any questions, you are very welcome.
Can I ask one naive question about the definition for the quantum difference equation?
Sure.
So basic question, what's this equation taking place in, like the both sides of the formula, if you can go back to that page? So it's psi times L, yes. So this is the equation, both sides are valued in where?
Both are some operators on K theory of Nakajima variety. So L is operator of quantum of classical multiplication by the tautological bundle. So it's diagonal in the basis of fixed points, and it doesn't depend on Z.
And psi is some operator that one trying to solve for?
Yes, psi is the general solution of the quantum difference equation.
Okay. And the okay, thanks. And the Q dependence occurs on the right-hand side through where?
Through psi and m, both depend on Q.
Okay.
Only L doesn't depend on Q.
Okay.
So this is like a K-theoretic version of Giventhals J function, roughly, but
okay.
defined via Andre's theory.
Okay, another question is that I see a lot of taking the limit Q goes to 0, where you can relate the elliptic case with the K-theoretic case. So is there some equation in the elliptic case that's analog to the quantum difference equation? Or I don't know if this is a valid question.
That's an interesting question. I don't know. It would be interesting to think about it, but now I don't know.
The theory is a little bit boring if you want to make something based on elliptic cohomology, quantum elliptic cohomology. I mean, in principle, you can do it, but there are very few theories that make sense. So it's much more rigid and less interesting in some ways.
It's more restrictive on the target variety.
Okay.
You can do it in principle.
Okay, thank you.
Okay, are there more questions?
Yeah, also I wanted to mention that this geometrically such a limit when we shift Keller variable by some non-trivial weight, by some weight from the wall, it corresponds to the degeneration of elliptic curve to some usually nodal curve, made with rational components. For example, for the AN example, this degeneration to curve like this.
Why is that? Oh, I see. Sorry.
Some coordinates.
Okay, so if there are no more questions, thank you, Yakov, for giving us an incredible talk, and see you everyone next Monday, I guess.
Thank you very much for listening and great questions and comments.
So Yakov, the subvariety you get is so you're taking the limit in equivariant variables of x.
Yes.
And so the subvariety you want is the one that's fixed by what? What's new?
By the corresponding character. Or maybe co-character, yes.
Okay. Should be obvious what one wants, but
variables correspond to co-characters, and we can consider fixed subvariety. Then in the limit we get K-theoretic slope 0 stable envelopes of that subvariety.
Okay.
Yakov, may I ask you to explain again your simple example? So you said that you have Hilbert scheme and you consider slope A over B.
Yeah.
The previous, if you go back 2 steps.
Yeah, how about you explain this in detail?
Here.
Yes.
And then somehow you relate B to the rotation of C2 over which the points live.
Yes. So this slope A over B, it belongs to pcar of x times r, that is h2 of x and r. So by the map kappa, this is mapped to the torus, like A factorial, acting on the x dual variety. So we get some co-character in that torus. So this lies in the Lie algebra of K, and we have a map from K to A factorial kappa. So then d kappa, it maps this element A over B to some generator, to some co-character in the dual torus. So then we can define fixed subvariety on the dual Hilbert scheme.
I have a somewhat different from Alexei and mine perspective, which maybe will make sense to Mina. If we wanted, so what is the slope A over B for us? At least in case when they have a, we can, half of the slopes we do not understand, but half we do understand. They're related to torus links. So for us, A has to be proportional. Okay, let me skip that. I think A should be proportional to B for us. Otherwise, I do not understand it. So we imagine a 3D theory, which is supported on D2s. And then there will be, just a moment, I'm a little bit confused. How many extra? Okay, let's say we have the full 11-dimensional theory, which is supported by the full 11-dimensional theory in which we have a stack of M2s, and those M2s have a shape of a disk cross 11th time. And then we have 8 extra dimensions, which are split into 4 and 4, or C2 and C2. And in one of those, we could place a torus link, which will give a boundary condition for that stack of M2s. And then if you do a reduction, so you go to 2A, and U1 in particular is rotating the points of those torus links. So after that, you see only the radial positions of those strands. You do not see the angular position anymore. Then the stack of M2s becomes a stack of D2s, and we have B twists there. And
slowly. Which circle? You say you go to type 2A on which circle?
So we use, so there is, so there are 2 extra C2s. Let me call them Calabi-Yau C2 and Taubnat C2. So we compactify by U1 rotating Calabi-Yau C2. And torus, does it make any sense? Maybe I'm not explaining it properly.
So your M2 brane is has a boundary on has a circle boundary on some Lagrangian that you consider from the construct from this torus link.
Yes. Exactly.
Torus knot.
And that Lagrangian is related to the torus knot.
Yeah.
This Lagrangian is placed in the Calabi-Yau C2. Sits there mostly. So we have C3, which is C in which disks sit, and extra C2. And then we have a Taubnat C2.
Are you spelling out the like all directions of M theory, or just the part in the Calabi-Yau threefold?
Sorry?
Are you spelling out all directions of M theory, or just so?
Yeah, all directions of M theory we have.
Yeah. So Taubnut is the extra four-dimensional space. Yes.
Yeah.
It's good.
And so if we put a torus link in the C2 of Calabi-Yau, then we will create a sheaf, a sheaf which will yield your stable envelope on the Hilbert scheme. So the Hilbert scheme will originate from Taubnut C2, and the torus link will create a sheaf. If you, how do you call this map? Boundary to bulk, in that sense.
I see. So you want to, right. So you want to go down to type 2A string theory on the circle in the Taubnut.
So we do not, so we compactify inner C2 of Calabi-Yau. We do not touch the Taubnut.
So we're just trying to get a Hilbert scheme, right? So we want to go down to, from M theory, we want to go down somehow to type 2A string theory, right?
Yeah, and so we're compactifying C2, which sits inside Calabi-Yau.
Oh,
yeah.
You want to do this one, okay?
Yes. So in particular, this means that you lose the angular coordinates of the points which give you the torus link. So the points are moving around, and that it's part of the compactification action.
Okay. But if you lose that, then also your M2 brims are no longer D2. They don't become D2 brims.
But this actually they will transversal. It's transversal to M2, so you get D2s.
Okay.
Because they're spread away from the center. So the action is transverse.
Okay, so you want to arrange it somehow. You want to somehow. Just a second. We had this discussion with. Yeah, you want to deform. You somehow want to deform from the usual toric setting, and that's fine. Okay. All right. So fine. Good. Yeah. Okay.
So somehow. So Yakov is saying that on the mirror side, somehow he wants to see taking the quotient by Z mod B. Apparently.
Well, he has an equivariant action, right, which is discrete, which is what he wrote here, right? So this will produce for him this quiver with the AB quiver somehow.
So what was the torus link with our choice of compactification should somehow, apart from compactification, should also create the quotient by Z mod B, apparently of the C2 which sits inside Calabi-Yau. I'm just trying to make string sense of turning slope A over B into taking the quotient by Z mod B on the other side. That's what I'm trying to figure.
So again, for him, this the being near a particular wall
maybe something like torus knots in length
means a particular torus action on the whole variety, and a torus action which looks like the matrix that he wrote in black.
Yeah, and I'm trying to.
And so if you ask what are the fixed points.
So first of all, his
of that.
Sorry. So when you do mirror symmetry, as far as I understand, then the Hilbert scheme, the dual Hilbert scheme, which looks like the same as the original, perhaps, reemerges as the other C2. the C2 which was related to the torus knot, to the torus link. I just wonder how, Yakov, you would argue that you have to take a quotient by Z mod B. Is there a precise way? Why would you take that quotient?
I mean,
You somehow, so you somehow you relate the property of the slope A over B on one side with the whole variety, which is Hilbert scheme over A sub B singularity.
Yes. Maybe it's easier to first relate if we consider shifts in just equivariant variables, and we don't need the dual variety.
I'm sorry, I'm not advanced enough yet to discuss your functions, unfortunately. I was just trying to visualize the string argument which says that on the dual side you're supposed to orbifold. Yakov, you're doing the orbifold, right?
Yes.
Why this orbifolding would match the boundary?
These equivariant parameters, right? These are some mass parameters, or like rather holonomies for some discrete gauge fields, and he has a discrete holonomy, which is the matrix. So if you ask what's invariant under it, this is the same as asking for your fields to satisfy the orbifold equations. So he gets this quiver. I think that's how it should go.
Okay, I'll have to think more. So it's puzzling to me, but very interesting.
So
and for me, it would be interesting to understand better your picture.
So you consider 11 dimensions, which is a 3-dimensional Calabi-Yau, another C2, which is Taubnut, and 11th time. And in Calabi-Yau, you have C cross C2. So you place a stack of M2s in C as a disk, and they also extend along 11th time. And then you insert M5s, which stretch along 11th time. They wrap cigar of Taubnut, and they're also 3-dimensional inside Calabi-Yau. But I think they mostly sit inside C2 of Calabi-Yau. So they create, it will be imprecise, but let me say it, but this should be corrected. In that C2, they look like this. They stretch along one C, and there are points in the other C. So they create boundary conditions for M2s because those points are away from the origin. So,
yeah, you want to move them off the origin, right? That's somehow crucial in the statements you're making about how circular reduction acts.
Yes, exactly. I have to keep them off the origin. And so as you go around the boundary of the disk, and they're also, and in the C of M2s, they are at radius R, let's say. So these M5s are at or how many dimensions? Yeah, 3 dimensions. So they form a circle in the C where the disk sits. They wrap one other C, and there are points in another C. And so as you go along the circle, these points start to move, and they form a braid, a closed braid. I didn't explain it properly. Let me, so suppose you have first C, second C, and third C. So first C, we will place M2. M2s, and the three-dimensional Lagrangian will be formed by a circle, by the boundary of the disk in the first C. It will be points in the second C, and it will wrap the whole third C. So the U1 action that we would use rotates the second and the third C.
Mm-hmm.
But prior to that, you could see a torus link formed by the points in the second C as you go along the circle. Sorry, Mina, I'm afraid.
I mean, I think your boundary conditions are roughly the same, but not precisely, right? Because unlike in this story that Yakov is saying, where preserving all the torus symmetries is crucial, for you, it's kind of the opposite. You have to break them for the story you're saying to make sense, right? And in fact, you do break them naturally, right? Your M5 brains, they're at some collection of certainly the place where the M2 brains attach, they move off the origin of the C, right?
Yes.
But yeah, I think that these are the kind of in the same family of boundary conditions, I suppose. Modulo the question of which symmetries you preserve. But I don't see that his formulas are going to be directly useful to you, precisely because the symmetries that are crucial to him are broken for you and so forth.
So the reason why I mentioned this is that if this boundary, this closed braid is a torus link of the type A over B, but A has to be proportional to B. So A is M times B. In this case, the boundary bulk map will turn this boundary condition into your stable envelope, into a sheaf which K theoretically will give you your stable envelope. In fact, you need several, so let me, at least one of them. So for me, and this, I think this matches what you were saying in the beginning of Yakov's talk, when you said that your stable envelopes come from boundary conditions.
I mean, you know, here you can so again, for abelian gauge theories, it's not difficult to even write down formulas for what these are and you know and so forth. The difficulty is, I suppose, when the theories are abelian, you can essentially solve it. The geometry, everything is so simple enough that you can just solve it directly. You don't need that much work in terms of, you know, understanding, for example, what these mother functions are and understand mirror symmetry well enough. But understanding this for non-abelian gauge theories in some way where, you know, physics would directly tell you, okay, well, this is what you should be doing. I don't have still, you know. In particular, this
I'm sorry, may I ask, yeah, maybe I misunderstood the whole story, then I apologize for, so what is the role played by this A sub B singularity? So the dual of Hilbert scheme is again a Hilbert scheme. So how does this, this more complicated quiver emerge? The one where you have red dots on blue circle.
So if we consider factorization of elliptic stable envelope of just Hilbert scheme for some non-trivial slope. We can do slope plus epsilon and slope minus epsilon. And the factorization will be K-theoretic stable envelope of just Hilbert scheme times some matrix depending on the Keller parameters. And this matrix is K-theoretic stable envelopes of zeroth slope for the dual Hilbert scheme. The first Hilbert scheme has equivariant parameter, say A, and the other has equivariant parameter Z. So these two factorizations, from comparing these two factorizations, we obtain the relation between the wall matrix of the first scheme and the R-matrix for zero slope for the second scheme. And from this, it follows that basically they are not depending not on A, nor on A, nor on Z. They are just functions of H bar, somehow conjugated by monomial matrices of A and Z.
But again, could you just say, what is the role of this A sub B quiver, which is blue circle and red dots on the picture that we have right now?
It is an invariant subvariety of the dual Hilbert scheme.
How is it a subvariety there?
So if we have cyclic group action, then instead of just usual Young diagrams for Hilbert scheme, we get colored Young diagrams. And all spaces, for example, this vector space N, it has decomposition into characters of the cyclic group. And the characters are exactly these B vertices. Here we have trivial character and so on. And the map X and Y, multiplication by X and Y, it can increase the character or decrease the character modulo B because of this action.
I'm
So
sorry.
the first
in case when N is equal to 2, and let's say B is also equal to 2.
Okay.
Can you describe explicitly how this complicated? So I know that in that case, the Hilbert scheme is just cotangent bundle to P1, and I can picture it in my head.
Yeah.
Can you explain how this complicated guy sits inside?
It's much easier than that. So just think about a Hilbert scheme, which is a quiver with a single node and one loop, right? And so this is basically, it's like the Kojima construction of orbifolds, right? So you will just conjugate all the elements of the, you know, the axis. So if the Hilbert scheme is like a commutator of X, Y, 0 or zeta or something, right? So you just conjugate them by this matrix, like lift it on to action of UN or something.
And what do you say?
You get this. There's a paper by Douglas and Moore from '98, which is where I learned Nakajima's construction from, where they would describe basically such things in detail.
But just could you quickly say, so you conjugate X and Y by opposite phases, and then what?
So you have to lift this matrix, the ZB action that he has, into a UN matrix, right? So basically get a n-dimensional representation of this guy, right? And there are some choices. What does it look like? So, well, what can it look like, right? So it can, so if this is an action of order B, this n by n matrix basically is, you can conjugate it to like identity, then, you know, B through the unity, B through the unity square, B through the unity.
The roots of unity.
Right? Yeah, roots of unity, that's right. And then, well, the only thing you have left to choose is like the sizes of these blocks. So N1, N2, N3, and so forth are the sizes of the blocks. So this is just a fixed point set of that action.
So you're saying that if so I act with this on the Hilbert scheme by conjugating X and Y.
You're quite literally looking at a fixed point set of that action. That's right.
And that will be this quiver.
That's right.
But it has a bigger dimension, doesn't it? Because ends will be smaller.
Ends will be smaller. That's right. Exactly. Well, the ends add up to the original n, right? There are lots of matrix elements which are 0.
Okay.
Yeah. So the things that come from, the things, the off-diagonal elements will give you. But the basic observation is very interesting about this limit of the stable envelope breaking up like this. That's something that one should be able to understand physically.
So you see that the stable envelope will break?
Well, he says if you take so q to 0 limit, right? You're degenerating the torus to a circle. But he says degenerated in a at some non-generic point. Then instead of just getting basically the partition, instead of your torus partition function just degenerating to a circle partition function of, I'm not sure how to precisely say it, because to say it precisely you would have to understand what it means. But it's quite a beautiful observation, and it's extremely powerful. These formulas that Andre had, that the two Andres had in their paper for the Hilbert scheme, and how they wrote the monodromy, was always puzzled me what it had to do with our monodromy. So he explains this. I just don't understand his answer yet, but it's beautiful.
Okay, thank you, sorry.
Yeah, so it would be lovely to explain this, what this actually means. I think by studying this question, one will actually understand better what the mother function is as well, and so forth. I mean, how to actually get to these things. Nice, really lovely.
Okay, thank you. I'm sorry for.
No, it's great you joined us, and we like lots of questions. So otherwise, Yakov's talk would have been too short. We usually at least do 1.5 hours, so we are now 1.5 hours. Okay.
Thank you very much.
Okay, thank you.
Thank you.
All right. Okay. Thanks a lot. Bye-bye.